Swayam Prabha. Digital India. Educated India.
Welcome everyone to this NPTEL online certification course, Techniques of Materials Characterization. So this is the last class, module 12, and we have so far discussed almost everything what was there in the syllabus. We discussed about the optical microscopy, we discussed about electron microscopy, we discussed in electron microscopy, we discussed about scanning electron microscopy, we discussed about transmission electron microscopy, and then we moved on to diffraction based techniques. Again there we discussed about electron diffraction, we discussed about X-ray diffraction, and in that module the 4 lectures we had before this, there we were discussing about how to utilize X-ray technique, X-ray diffraction technique for materials characterization, various things, effect of strain, effect of grain crystallite size, and so on, amorphous materials versus crystalline material, all of this. So we are done with all this 59 or all these lectures until up to now. We are almost done. So I thought that this last lecture I will introduce you to a very special technique. Why it is special, we will discuss about that, but to me it is very special because this is one technique that we use, my research group they use, and I also used it over my research career very extensively. So this technique is called electron backscatter diffraction, EBSD. So we will be just discussing about this special technique today, and we will be discussing about, of course, EBSD and its working principle. And in order to understand the EBSD results or how EBSD works and what data you get out of EBSD, how you can analyze the EBSD data. So to do all of these things, you have to have some idea about orientation, what is called orientation of something, or more general term, maybe you have heard about this, crystallographic texture. If you are a material scientist, you must be aware of this term, texture. So what is texture or orientation? And then we have to understand Kikuchi pattern, because that is what is the main signal in case of an EBSD technique, and then indexing and orientation determination in an EBSD, and finally we will take some specific examples about EBSD, what EBSD can do, and so on and so forth. Okay. So why EBSD? First and foremost is simplicity. It's a very simple technique, it's a high-end characterization technique, and over my entire research career I have realized that this technique, if it is used by someone who has a very good knowledge about characterization technique and material science, they can do wonders with this. So this can be very well compete with, let us say, other high-end characterization techniques like electron diffraction or transmission electron microscopy or X-ray diffraction and so on. So it is very powerful technique, high-end characterization technique, but it is a very simple technique as well. So it can be used or can be fitted in a scanning electron microscopy. Most often that is how you used to see it, though it can be, EBSD can also be used in like a similar technique can be there in transmission mode, but mostly we will be discussing today about EBSD, which is used in a scanning electron microscope. So it comes as an additional detector, and almost every scanning electron microscope you procure these days with a little extra money, you can also get this electron backscatter diffraction. The sample preparation is very easy. That is another very attractive point. From the bulk material, you can prepare sample quite easily. It is not as extensive sample preparation, possibly not as easier as it is in X-ray diffraction, but definitely it is much simpler than preparing a transmission TEM sample. High speed of data acquisition, very high amount of data you can collect within from a reasonable area, statistically significant area, to be very precise in scientific terms. You can get a data on a statistically reliable scale. That is one of the major drawback of transmission electron microscopy. There the data that you capture is very nicely spatially resolved, but not statistically reliable. On the other hand, if you capture data, orientation data, diffraction based data, if you capture it from an X-ray technique, you can have a very good statistics, large area, very good statistics you can have, but you will be losing that spatial resolution. That means the connection with the microstructure, this is not so easily done in an X-ray technique. So, EBSD is somewhere in between. Obviously, also the different range of information that you can get from an EBSD, from the same specimen area you can get information about crystallography, orientation, microstructure and phase, everything. All this different type of data you can have. You can also couple it with complementary information, you can also couple it with complementary other characterization techniques, like you can couple it with EDS or WDS techniques. So, you can get chemical information and you can get also orientation related information and crystallographic information, and you can club them together. So, all of these things make EBSD a very attractive technique for many different fields. I just named some few here, but the list is only increasing over the years. So, metal processing, aerospace, nuclear, automotive, microelectronics, earth science, geologists, they use EBSD a lot these days, and even biological materials also slowly people are realizing. Of course, biological materials has its own limitations and all, but slowly some biological materials people are also trying to apply EBSD for that. And you can, if you go by materials, what are the kind of materials you can use with EBSD? You can have metals, alloys, intermetallics, ceramics, thin films, geological materials, semiconductors, you just name it. And that is because you can get all this different range of information out of EBSD. You can have crystal orientation, misorientation, grain size you can calculate, global texture, bulk texture you can measure, local micro texture you can get, you can, if it is a deformed material, how much percentage of recrystallization happen, dislocation substructure analysis, strain analysis, grain boundary characterization, all different CSL, coincidence site lattice boundary, you can have information about that. So, all of these things you can get out of EBSD, that is why it is so diverse. Now, as I said, in order to understand EBSD, you have to understand orientation. What is orientation? And in simplest term, orientation is basically location, defining location of certain things, and that means it is basically an interrelation between coordinate systems. So, how is it so? And a simple example of that, I would say that most of you have possibly studied coordinate geometry. I studied it and it was very, I was very passionate about coordinate geometry in my +2. So, in coordinate geometry you have this kind of a coordinate, you can define it as x, all of us done that, and then if you define a point out here, you can have its coordinate in terms of x and y, right. So, x means this is what and this is your x and this is your y. This x and y basically tells you the coordinate of this point. That means you first define this coordinate system, if it is a Cartesian coordinate system, polar coordinate system, whatever. So, you define this coordinate system and then in terms of this coordinate system you define this point. So, this x and y basically tells the location or orientation of this particular point with respect to this coordinate system. If you change the coordinate system, if you make your coordinate system like this, let us say this is I am putting it x dash y dash. Now, its orientation becomes, let us say something x dashed y dashed, where this is your x dashed and this is now the new y dashed. So, if your coordinate system change, orientation, location, everything changes. So, this interrelation is called orientation. How it works in terms of, let us say we will take a simple example of, let us say, any metals and alloys, that is easier to understand. So, how it works? There also you have this coordinate system where you define the processing or materials, two different coordinate system we define. One is called the materials or specimen coordinate system and one we call it crystal coordinate system. So, specimen coordinate system, if you take example of something like a rolling, so you have this rectangular piece where this is defining as the rolling direction and this is the normal direction and this is the transverse direction. In a rolled sheet, if you take a rolled sheet, this is how the three principal directions you can get. Okay. So, with respect to that, if you define your crystal, these are different grains, this is a polycrystalline material, you have different grains, and now what you can think of is that how these grains are all oriented with respect to this coordinate system, rather which plane or which directions are oriented along RD, which direction is oriented along ND, which direction is oriented along TD. That will give you the orientation or texture, that is what we call. So, this is one type of material where all the grains will have similar kind of orientation. These unit cells are showing that all the grains are having similar kind of orientation, whereas this is one material where different grain has different kind of orientation. So, this one is textured, this one is not so much textured, that is what. So, this is again I define the sample coordinate system in terms of a rolling symmetry, and I have now checked what is the crystallographic symmetry, how these two are oriented, which direction is parallel to rolling, which direction is parallel to normal direction, which direction is parallel. There is even more complex way of defining that, where your specimen coordinate system can be arbitrary, and what you define there is called Euler angles. You basically define 3 angles. Those 3 angles will tell you how you can bring the specimen coordinate system and crystal coordinate systems in coincidence. So, if you start with a complete arbitrary orientation, your specimen symmetry is something, crystal symmetry is something, how you can bring them coincidence, and you will find out mathematically it can prove that you need 3 definite type of orientations. With 3 definite type of orientations, you can bring them coincident. What is those 3 angles will define the orientation of that particular specimen. This is called Euler orientation. I am not going into that. You can go through any texture textbook or any texture related course to understand what I am talking about. Just to tell you, this is very, very general, and one example I have shown here that this Euler angles are even used to define the location of any aircraft. So, if an aircraft is flying, what with respect to the coordinate system, earth coordinate system, how it should rotate itself. This is one is called roll, one is called pitch, one is called y. So, how it should rotate, which angle it should rotate to align itself with respect to the coordinate system, earth coordinate system, then only it can find its position, it can find which direction it should go, and so on. So, these Euler angles are very, very important even in aerospace. This is a very general, this is how you can define an orientation. Okay. Orientation, why it is important? Because it defines all your different properties. So, you can see that this Young's modulus of titanium alloy, this is something to do with the titanium alloys. So, this Young's modulus of this titanium alloy will be changing with respect to the orientation. It is something, if the single crystal of titanium is oriented along RD, then C axis, basically the C axis, if it is oriented along RD, you will get some Young's modulus, but when that is aligned with respect to say TD, you will get something else. So, your entire Young's modulus is changing depending on the orientation. Okay. So, orientation influences all of these various different properties. That is what the importance of orientation. Okay. Now, we talk about something called Kikuchi pattern. So, Kikuchi patterns is basically the heart of EBSD. That is a signal, as I said, how it works, how the Kikuchi pattern works. So, Kikuchi pattern, what happens is when an electron beam hits a specimen, okay, and we understood, we already discussed that when in a scanning electron microscope, let us discuss only a scanning electron microscope. So, in a scanning electron microscope, when the electron beam hits the specimen, it generates backscattered electron, and the speciality of backscattered electron is it is a elastically scattered electron. That means it has a definite wavelength, and if the source does not have a definite specific fixed wavelength, it will not be useful for diffraction experiments. We discussed about that. That is why anything other than backscattered electron will be useful for diffraction related experiment in a scanning electron microscope. That is what another big sort of, I would say, speciality about EBSD, because it is the only technique in scanning electron microscope which will give you diffraction related experiments, which will be giving you crystallographic information about the sample. All other signals will give you various other, like for imaging, for chemical analysis and all, but diffraction related experiment you can only use backscattered electron. Okay. So, these backscattered electrons are generated from deep within the specimen, and when they are coming out, they can sort of, then those backscatter electron will be used as a source and they will be getting diffracted by crystallographic plane, and then when this diffracted beam comes out, it will form something called Crocel cones, like this cone, they will be coming out. This is pretty similar to the X-ray diffraction. You just remember and go through the X-ray diffraction, this is, you will be able to understand this. This is the Laue diffraction pattern, the way it forms. And if you keep something like a phosphorescent screen in front of this, like this, if you keep a phosphorescent screen here, then this Crocel cones will be cutting through the screen and producing this kind of lines, which are called Kikuchi lines or Kikuchi patterns, after the name of this person who has seen these lines all the way back to 1928. So, this is the first Kikuchi pattern that was recorded from a calcite, and obviously that time that resolution and other things was not great. These days we get Kikuchi patterns in this way, and since it is created, this pattern is created from a diffraction experiment, it has all crystallography information like zone axis, it has all symmetry related information, everything. Kikuchi patterns are also generated in transmission electron microscope. So, we have seen this example, I have shown you this when we were discussing about TM, I have shown you how this entire stereographic triangle orientation triangle was generated using this Kikuchi patterns here. Okay. So, this Kikuchi patterns basically generate two lines, it is an amalgamation. So, any one set of plane generates two lines. So, this one line top and another line in the bottom, and together they generate this Kikuchi band, and these bands collectively, all the bands will generate this kind of a Kikuchi pattern. Okay. Fine. Now, what you have to do is basically in SEM, this is what your electron beam is coming like this. We can look at here, the electron beam is falling on the specimen, this is your specimen, and they are generating this Kikuchi bands, and you have the detector over here, which is a phosphorescent screen basically, and this phosphorescent screen will create this Kikuchi pattern. So, you are basically creating this entire diffraction. So, there is this 3-dimensional 360-degree cone of this diffraction pattern that is happening here. This is a this Crocel cone, 360-degree Crocel cone which is generated, and you are just capturing only a part of that in a 2-dimensional detector plane. So, and there it is forming this Kikuchi patterns, and many a times I get questions that why this tilting is there. Just go back to your SEM principle, there it is very clearly said that if you increase the tilting angle, then your backscattered electron yield increases, or rather there what happens, the interaction volume remains the same, but the distance between the specimen surface and the interaction volume, that from where this backscattered electron generates, that decreases. That means those backscattered electrons which are of low energy, of course. So, those backscattered electrons can very easily come out from the surface, and that is why electron backscatter, this EBSD technique is also very surface sensitive. So, this information is generated from a very small depth, even though the backscattered electrons are generated from a large depth inside the specimen, much larger than the secondary electrons, but still the backscattered electrons, when they are coming out from the specimen, in their path they will get diffracted. That is why the diffraction patterns are almost generated from the surface or very small depth of the surface. Okay. Now, you have to interpret these Kikuchi patterns, okay, and get the crystallographic information out of it. So, in order to do that, we utilize some of these properties of these Kikuchi patterns. So, basically this Kikuchi patterns, as I said, the bands represent one set of crystallographic plane, okay, and wherever there is a intersection of these bands, basically that is the zone axis. Remember the definition of zone axis. So, the intersection of these bands means the planes in the real specimen, basically this is the intersection of the planes. Those planes only are diffracting, and that is what is represented in Kikuchi pattern. So, where the planes are cutting through or intersecting each other, that is represented in a Kikuchi pattern like this, and this kind of intersection, and that is the zone axis for those. So, if you define this zone axis now, you will be able to get this entire Kikuchi pattern, you will be able to understand the entire Kikuchi pattern. You can understand that which of this, what band is this, or rather from which crystallographic plane this Kikuchi band is generated, from which crystallographic plane this other Kikuchi band is generated, and so on and so forth. That is what you are trying to get. How you are going to get that, we will discuss. It is not so straightforward. Okay. For that, you have to know a lot of information about the specimen. You have to know what kind of a specimen a priori. If you do not like, that is true for all high-end application or high-end characterizations like TM diffraction pattern analysis. If you do not know exactly what material you are going to or you are studying, what is the symmetry of this material, then it will be very difficult to even understand this Kikuchi pattern. So, any chemical information you must have about your before starting this pattern indexing point, you must have some idea about your material itself. Okay. Some few things important, like for example, despacing. Okay. So, basically what happens, this distance between these two Kikuchi lines, that means the thickness or width, whatever you call. The width of this Kikuchi band represent the d value or d spacing of those planes, because as I remember this, I said that two Crossel cones are generated from any one set of plane. You can think of that like it is generated from this plane, it is generated from this side and that side of it, front side and back side of any crystallographic plane. So, basically that is the width of the Kikuchi band is representing the d spacing of those bands. So, the planes which are having, just like the diffraction pattern, remember the diffraction pattern, TM diffraction, there also that d spacing was the distance between the central spot and the spot that is generated corresponding to any crystallographic plane. Exactly the same thing here, the distance between the two Kikuchi bands is basically the d spacing for that particular set of planes. So, you will have in a Kikuchi band, if you look at the Kikuchi band or Kikuchi pattern, you will see that bands are not of the same width, because their d spacing is different. Different crystallographic plane has different type of Kikuchi or different type of d spacing, and then they will have different width in the corresponding Kikuchi pattern. Okay. So, that is one. Second thing is, and then I leave a question to you to answer this, that high index planes versus low index plane, which one will have higher Kikuchi width, and from there, that is another important point when we do the indexing, that is another important check that we can do. Anyway, also since this is a diffraction pattern, equivalent to a diffraction pattern, it will have all symmetry related information. So, that is another way of checking it. Okay. For Kikuchi pattern indexing, basically what you wanted to do is an automatic indexing. So, if you have this kind of an index, this kind of a Kikuchi pattern, you can sit with this material information and you can look, then you can try to identify, just like a diffraction pattern, solving a diffraction pattern, you can try to solve it, and it is possible. You can do, I mean, you can have a library function, you can have various library, you can know that if this is the crystallographic orientation, then this kind of Kikuchi pattern I should get, and so on. Otherwise also you can possibly figure it out, that solving this one. But in a scan, as I said, you want to get a data from a statistically reliable scale. So, you want to get a data from a large area which will contain many millions of pixels, and each pixel here giving you one Kikuchi pattern. So, indexing those Kikuchi patterns manually is impossible. That good old days people used to do that. 1990s, I was talking to somebody couple of days back, and he said that in 90s when they were doing EBSD, they were basically indexing this kind of Kikuchi patterns manually. Now, it is completely automated, and the automation, one of the way you can do this automation, you can bring this automation by doing a mathematical transformation known as Hopf transformation. I am not going basically what is Hopf transformation. It is a mathematical operation by which these bands are transformed to a point in Hopf space, just like a Fourier transformation, and then indexing becomes much easier. You can use library function. Okay. So, once you do that, basically different grains you can go, and Kikuchi pattern corresponding to that orientation of that crystal planes, you will get different Kikuchi patterns. Fine. Next step is indexing to orientation determination. You have indexed the Kikuchi pattern, done. Now, orientation determination. As I said, orientation is an interrelation of coordinate system, and basically here the coordinate system means the specimen coordinate system, how the specimen is oriented and how the crystal planes are oriented, and then bringing them to coincidence in terms of coincidence basically to determine this Euler angles. That is what you need to do, and for that you have to do a lot of calibration. There is something called pattern centered determination, which again I am not going what is pattern centered determination, but that is how you basically can understand this Kikuchi pattern. After indexing, you can figure out that how these grains basically, each of these grains, how they are oriented with respect to the crystal specimen coordinate system. Now you have just defined the crystal coordinate system, but after this you want to determine the relationship between crystal coordinate system and specimen coordinate system. That you can do by again completely automated way you can do this, and for that you have to do this calibration and all so on. Okay. So this entire process, as I said, known as automated indexing and orientation measurement, and this process is completely computer controlled these days. So you can basically get this entire process, this entire Kikuchi pattern determination, right from capturing a Kikuchi pattern to Hopf transformation to indexing the pattern and finally to generate the orientation data or Euler angle. So this is 4 step. First you generate the Kikuchi pattern, then you do a Hopf transformation. This part is only real, this is only the hardware part where the beam is generating the Kikuchi. So this is what you measure basically. After that, this all 3 parts is software related, computer controlled. There is nothing to do with the measurement itself. So you generate this Kikuchi pattern, you do the Hopf transformation, software does it for you. Software then look up a table. Basically you generate artificially, you can generate this Kikuchi patterns and then you match them, and finally you can generate this orientation information, basically the Euler 3 Euler angles you calculate, and that is done. This is how the EBSD basically works. Okay, and this entire, as I said, entire pixel, this entire process you can do it these days in milliseconds. So a large area containing millions of pixels will not take more than few hours for you. If you have to do, if you think that even something, when I started my journey in way back in 2006, when I started doing this EBSD, this kind of data takes almost million pixels, means almost days will be taken in a scan. These days you can do it with faster detector, with lots of software improvement, computational power improvement, you can do it in few hours itself. Okay, but the basic principle remains the same. These 4 steps you have to recall and remember. Okay. Now this is how the EBSD data comes out. This is the output. I am showing you a real EBSD data output. So this is how the Euler angle, this first three data, this is a data, EBSD data. If you open it in a text file as a text file, this is what you are going to see, the first 3. So this each of them is basically is a pixel, the information in a pixel. So all of these pixels you have, like it will tell you X and Y definitely in a specimen. Within a specimen, what is the X, what is the Y, that is the location of that pixel. Then what it will tell you is Euler angle, 3 Euler angles. Okay, so these are the 3 Euler angles for that pixel. So that pixel, the crystal orientation is such that you have to rotate it in this 3 with along or this 3 different angles. If you rotate, it will come in coincidence with the specimen coordinate system. So that is what you can determine, and finally this from here, from this data, again you use software analysis software, various commercial softwares are available, various free softwares are available, MATLAB programs are available also. You can develop this kind of maps, or you can also develop this kind of a texture information and various other things you can do with this data itself. So this data gives you, as I already mentioned, data gives you orientation information, but as a function of microstructural detail. That is the power of EBSD. It gives this entire map, basically represents the orientation of microstructural features. You can imagine that these are the grains, and this color coding is basically giving you the orientation of each of these grains. That is the power. That is where it is different, or it is a higher end characterization compared to an SEM. So SEM will only give you this image, it will not give you any information about orientation, plus it will not give you information about phase. Here you can also identify from the diffraction, since it is a diffraction technique, you can identify the phase. X-ray will possibly able to give you this kind of a texture information, it will not be able to generate this kind of a map for you, and that too in a statistically reliable scale. You can see that this is almost, you have measured around few millimeters, okay, around 5 millimeter by something like 2 millimeters or 1.5 millimeters of area you have measured within your specimen. Okay. What EBSD can do, I am not going in details. Again, this is some results that I have in my research career. I have used EBSD for various type of materials problem, and just a glimpse of that. If you want to know, please write to me. I can pass you, or I can suggest you the corresponding publications. You can read about that. So, I have used them for something like phase transformation. So, this is one titanium alloy, two-phase titanium alloy, and how the phase transformation happens from high temperature BCC phase to low temperature HCP phase, how this phase transformation happens, what are the mechanism, what different type of microstructure it forms, so on and so forth. Those kind of studies you can do, because it can give you information. Again, as I said, it can give you information about crystallography, and from there you can generate something called orientation relationship, everything. You can also study deformation of materials. This is one extreme example I have taken, where I have used EBSD for measuring mechanisms of superplastic deformation, high temperature deformation. Those mechanisms you can get by EBSD technique. Okay. Normal thermomechanical processing, people regularly use EBSD to find out the mechanisms, to find out how microstructure develop, how the texture develops, so on, and you can use it for any other metallurgical or materials related problem. Like I have used it for fatigue of nickel superalloy. There we were able to simulate kind of a grain growth. We were able to see something called macro grains, or this grains or grain cluster of grains which are responsible for fatigue crack generation under high cycle fatigue conditions. Okay. So, those kind of studies also EBSD comes out to be very, very important for them. So, these are a couple of examples. Finally, these are my concluding remarks about EBSD. First of all, EBSD is unquestionably the fastest and most reliable way of acquiring data for any crystalline materials. The only problem is you can use it, since it is a diffraction based technique, you can only use it for a crystalline material. If you have an amorphous material, it doesn't going to help. But these days we are even trying to use it for an partially amorphous, or something called glass ceramics, where one of the phase is a glass, one of the phase is a crystal. There we are trying to get the orientation of this crystal phase using this EBSD technique. So, that kind of system you can use it. So, of course, as I said, it is very fast because of this improvement in all this automation coming up in there, and you can do it in a statistically reliable question. Traditionally, many of this characterization which people used to do by optical microscopy, SEM, TEM, X-ray, and so on and so forth, all of these things you can replace all this characterization routine by one single EBSD scan. It is possible. You can get every kind of information from this EBSD technique. Hardware part of EBSD is very, very well set, and faster detectors. Every other day I get to hear about some faster EBSD detector, where acquisition speed is much higher, where the resolution of spatial resolution of this phosphorus or phosphorus, this screen is getting better and better, and those kind of, and then increase of computational power obviously. So, all of these things is a very, very well set. Softwares, the theory of this EBSD, that is also very well set, and improvements are happening. People are trying to do many more mathematical treatments on the EBSD data, how to get better pattern center calibration, how to get Hopf transformation much better, and so on and so forth. So, the software part is also very, very sort of well set, and the data acquisition, data analysis has become very fairly straightforward. So, if you are working on a deformation related problem or the traditional problem where EBSD people are using from last 15-20 years, it is very, very well set. It is like a routine analysis. Obviously, in newer techniques, if you want to use it in newer research problems, that is still a challenge, but that is all the fun of the research. Okay. Newer developments, as I said, are buzz, faster detector, innovative informatics, newer analysis. And the biggest prospect, as to me, I mean, as I said, this is all coming out of my experience of working with this technique over 15 years now. Applying this technique in various unexplored field of research, like one example I have given you, ceramic materials. We are using this one in something like glass ceramics, and coatings, thin films, all these places, microelectronics, many people I have seen using this to know the texture of the thin films and so on. And this is what my final remark to everyone who is listening this NPTEL lecture, that you know this technique, the EBSD technique, it can do much more than what you think. If you are interested, please you can contact us back. And I have here given some of the very latest techniques that people are trying to do in the EBSD field. For example, 3D microstructure. So, this is called dual beam system. So, you take EBSD scan over one surface and then you remove the surface, and then you can take another EBSD scan from a lower depth, and so on. You go through in the Z direction and you finally develop this 3D microstructure. Coupling EBSD and chemical analysis, this almost fairly become very routine these days. It's not nothing new. Almost last 10 years people are using this, and it has become very, very common, but it can give you lot more than normal EBSD information. Transmission ki kuchi in SEM. So, this is something called TKD, transmission ki kuchi diffraction within SEM. So, where you are using a transmission TM specimen within an SEM and you are trying to get the Kikuchi pattern out of it. That is something which is really a recent one, and people are trying it for last, I would say 15, 16, 15, 5, 6 years. People are trying to use it, and this can be really a very good technique where you can get advantage of TM as well as. So, the resolution is of that level in TM level, and you can get information instead of using TM based electron diffraction, you can get the EBSD. So, you can scan a larger area and faster, much faster. So, with this we are stopping it here. Thank you all for attending this course, and I wish you all the success for your future endeavors. Thank you.